First, I want to welcome everybody. Thank you for coming out on your busy evening and coming to join us here at the Silicon Valley Deep Learning Group. We have a wonderful speaker tonight. We have some other interesting news as well. I want to thank you all for being here, and for those of you who are watching at home, we're at Juniper Networks right now, who are our gracious sponsor, who have provided us this room and the pizza and the rest of the wonderful environment that you're enjoying. I'd like to call up Nosh Minwala, who is part of Juniper Networks, and ask him to say a few words. Hey, Nosh, here you go. Thank you.
So thanks, everyone, for coming over. This is a shameless plug on Juniper. So a lot of you people may or may not have heard of Juniper Networks, but let me just summarize. Statistically, every time you use your web browser, those packets are touched by many Juniper Network devices in service providers. Every time you use a deep learning model served out of your favorite hyperscaler of choice, chances are those packets have been touched by Juniper routers deep in the hyperscaler's backbone. So our business is basically threefold. We build large-scale routers, switches, and firewalls. Within those, our systems are getting very large distributed systems. So like a big Juniper router will do 80 terabits per second. So if you could hold the entire internet within one room, you might need about 10 of those devices to run the entire internet. So they're getting pretty big. As a consequence of getting really big, they're becoming very expensive to troubleshoot and debug. And the failure domain of, say, a Juniper router could mean US East going down, literally the entire eastern seaboard, Amazon, everything else. So we are recruiting for people skilled in data processing, so data engineers, across log streaming telemetry formats. Also, unstructured formats are very prevalent in our systems. So anybody good at NLP, we'd love to hear from you. And then secondarily, we're also looking for talented data scientists who are interested in solving pretty hard problems in the domains of performance management, fault management, and health monitoring overall. Okay, with that, that's the shameless plug over. Now the interesting stuff. Thank you.
Thank you, Nosh.
I'm sorry, I will be posting job descriptions for this.
Okay, so let me also call up a couple other folks. This is sort of a big announcement, so we got a big crew of people that I want to bring up. I want to introduce you all to Herman Ross, and you all know Sophia Vickland, and you know Steve and you know Chris, who have been helping us build the Silicon Valley Deep Learning Group for now 3 years, I guess, running. So the Silicon Valley Deep Learning Group is now joining forces with the Open Source Vision Foundation. Is that right? Open Source Vision Foundation, OSVF. Now, okay. So what is OSVF? OSVF is OpenCV, which I've been working on for many years, as many of you know. The Open Source Vision Foundation is Open3D, which is another very sophisticated, very brilliant package of open source software that a lot of people have been using in a lot of their vehicles and drones and other kind of robots and every kind of thing like that. And then what's the last component? It's Carla, right? So Carla, OpenCV, Open3D, and the Silicon Valley Deep Learning Group are all kind of joining forces to create the Open Source Vision Foundation. And OSVF is going to be able to provide the kind of software tools that you're used to seeing from OpenCV and Open3D, and the community support that the Silicon Valley Deep Learning Group has. And of course, deep learning is now playing a large role in all of those other components. I don't know, Herman, you want to introduce yourself briefly and just say a few words about OSVF? Not to put you on the spot, but, since you're here.
Okay, thank you. Yeah, so we are very proud to have the Deep Learning Group joining our Open Source Foundation. Our mission is very much like broadcast knowledge on machine learning, deep learning, and computer vision to everybody. So we're trying to bring like state-of-the-art tools out there for people to use, for researchers, for engineers to be able to solve their own problems and to do the research. Basically, we're trying to democratize like important state-of-the-art parts of related to deep learning, autonomous driving, computer vision, and so on for everyone. So, well, thank you very much.
Welcome. Okay, so the meaning of this will unfold over the coming months as we are able to offer new kinds of events and new kinds of services and are able to bring together the teams from these 4 open community projects. So look forward to it. There's a lot of exciting things coming, and we'll be, at this particular venue, we'll be able to announce some of them first as they unfold. So now, okay, without further ado, let me introduce our new speaker. This is Gopal Erinjippurath, and Gopal is going to talk about object detection and satellite imagery. For those of you who have been with the Silicon Valley Deep Learning Group for a long time, we've had several talks on satellite imagery, and they've been really very interesting. Some of our most interesting talks had to do with analyzing of satellite data. So I'm very excited to invite Gopal up. So if you give him a great big hand, and he's going to come in and tell us what he's doing.
Thank you, Adrian, for your glowing introduction. And thank you all for being here. It's exciting to meet some of you before the talk. And big congratulations to Sophia and the team at the Deep Learning Silicon Valley Group and also the Open Source Vision Foundation for their merger. I think that's a big milestone. So when I first got introduced to Sophia a few months ago, she was really keen to get me to come speak over here. And we were talking about topics. And one of the things I realized is very often when you think about deep learning, you think about models and layers and lots of complicated convolutional networks or time series networks. But often one of the things that you forget is that to power those very data-hungry models, you need to collect clean data and organize clean data and take it from heterogeneous sources to homogenized, structured collections. So I thought that's something I can share some more of some of the practical knowledge on. And I won't talk too much about models, but I'll give a quick introduction on what works and what doesn't work in satellite imagery, at least from my experience. So a little bit about me. I've worked in Silicon Valley for a little over 10, maybe closer to 15 years. I started in the imaging space, working on high dynamic range imaging. So those of you, I worked at Dolby for many years. So those of you who heard of Dolby Vision, I was part of the early engineering team that brought that to life. And since then, I've transitioned more into machine learning and statistical learning techniques and mostly on vision and imagery-related applications. So this has been a very exciting realm of work that I wanted to share with you all about. So quick agenda. So I want to give you guys an introduction to Planet. I think you'll find that compelling. And that'll provide some context around how data sets are created. We'll go through an example. I'll talk about how we characterize performance for models on satellite imagery. And then I want to touch on what we call spatiotemporal analytics in the context of object detection. And then maybe give you a few examples of like integrated applications. And then I can tell you about a few active research frontiers that I feel are like very important in this space. So, the word mission is a very overloaded term at Planet because our founders come from NASA, and the word mission there has like a very specific context. So, the mission the company was founded with in 2011 by a bunch of former NASA scientists was to image the Earth every day and make that data accessible, actionable, and visible. So that's the mission they've been rallying around for the last 7 years since our founding. So we're close to 500 people in a few different locations across the world. We have sales offices in other regions like EMEA and APAC as well. And we also have an office in Mountain View. So a few years ago, we acquired some assets from a company that Google actually acquired. I'll tell you more about that. So our constellations have been engineered with a certain engineering goal in mind. We want to cover the entire globe. We want to have frequent revisit, and we want to make the imagery accessible. So that's the basis on which we build our satellite program. And that led to 3 different constellations. So right in the center, there is our flagship Dow constellation. We have upwards of 180 satellites in orbit today, which is the largest constellation of Earth observation imagery satellites that exist in human history, and they're all active. In addition to that, we've also acquired the assets of the Rapid Eye constellation, which is a much more of a legacy system that's still in orbit that generates or medium resolution imagery. And then we have the SkySat satellites. So those were what got rebranded as Terabella past SkySat's acquisition of Google, and then we acquired those assets from Google a couple of years back. So with those three satellites, satellite constellations, we have the ability to cover the entire Earth every day at high resolution. So here's a description of our flagship satellite. It's relatively small, so most of the times when we talk about satellites and like the traditional historic picture of a NASA scientist getting into one, it's like this massive sort of satellite. These are relatively small, so they're called CubeSats. They're the size of a loaf of bread. It's a good analogy, and they're relatively simple compared to some of the satellites that have been launched by bigger companies. Still complex in its electronics, but it's basically a telescope in a box with a camera and with an antenna. So that's a simplified way to look at it, and the rest of it powers that imaging system. So this is the launch that we did with the PSLV rocket, which was launched out of India on the 14th of February, 2017. So this was the largest launch in human history. We had 88 of our satellites launched into space, and what you see here are the satellites getting launched out of the rocket, each one of them being a DAO. And they then went into orbit, and now they're actively sending data back to our ground stations, and those ground stations are then powering the cloud. So out of 104 satellites, 88 of them were planets. So here's an example of what a satellite, when it goes off nadir and looks at the Earth from an angle, looks like. So here we actually pictured that particular launch from another satellite. So you can see the explosion and the satellite or the rocket launching into space. So it's a video of that. So this is essentially what happens when the satellite goes into our satellites go into space. They essentially form a constellation, which is akin to a string of pearls around the Earth, and they're in a sun-synchronous orbit, very close to the polar orbit, and they kind of function like a line scan on the Earth. So as they cross different regions, they're imaging. And then we have a fairly sophisticated tasking and image aggregation pipeline that stitches this all together based on the locations on which it's actually capturing imagery. So this is an example of our internal tasking software. It has less to do with deep learning, but I just want to say that one of the things that is really hard to do in satellite technology is the tasking of satellites and making it be at a certain point in a very precise fashion on the Earth and having that ground lock. And then being able to task a collection of satellites in a sequence such that over the course of an entire day, you're able to image the entire Earth or the entire land mass of the Earth at the resolution that we want. So this is essentially the collection of all the satellites that are currently in orbit. On the top, you can actually see the different DAO revision numbers. So we actually took the agile approach, just the same way we release releases of software. We actually have releases of satellites. And you can see two different orbits. There's the ascending and descending orbit, and those together form the constellation that does all the imagery. Okay, so that leads us to the Imagery Catalog. So this is the largest catalog of Earth observation imagery that we have through API access. You can get a trial key at developers.planet. And the way to look at this is there are those three satellite constellations. They're all at like different ground sampling distance. And the first level, what's called scenes and tiles, they're essentially imaging products. And you have different kinds of branding structures that are supported. That includes the RGB visual space and the near-infrared band. And in addition to that, the Rapid Eye satellites also have something called a red edge which is very useful for precision agricultural applications. The SkySat constellation also has a panchromatic band. So those of you who worked in satellite imaging, you know that the panchromatic band allows for like an image processing technique called pan sharpening that allows you to make the RGB imagery sharper and thereby improve the resolution of the imagery in the colored bands. So that's something supported in SkySat. So this is what the spec sheet for the imagery looks like. And this is all public domain knowledge. So the thing to note here is SkySat is sub-meter, and because of the pan sharpening, and also because of the inherent resolution of the sensors. And the Dow constellation centers around 3.7 meters in terms of ground sampling distance. So that essentially means between 2 points on the ground, which are mapped to 2 pixels in space, adjacent pixels in space, you have approximately 3.7 meters.
Gopal, is there any international standard that governs which areas can?
There are. So there are some standards around that and what resolutions you can scan it at. So in North America, for example, my understanding is you cannot scan for anything lower than 30 centimeter ground sampling distance. So that's why all commercial and semi-commercial satellite operators kind of are bounded by that lower limit. So this is the coverage over a single day in April from our satellite constellation, in particular the Dow. So you can see that it covers a significant amount of the landmass of the Earth. The oceans are still relatively complex and a huge area to cover. So the tasking is what enables this to happen. So almost every day you have like a mosaic of the Earth that we can actually detect change on. And that's the fundamental value proposition from our imagery. So through those efforts in the last 7 years, we've actually achieved mission 1. We are able to make the data accessible, actionable, and visible. And we have a tool called Planet Explorer. All of you can like sign on to, and you can see imagery of the entire Earth. And it also allows you to like go back in time and look at the catalog over different days. So mission 2 is essentially space plus AI. That's essentially, I believe, what's inspired many of you to come here. So it's bringing together our knowledge of what's happening on the Earth along with daily observation of satellite imagery to bring together new possibilities for making the functions, so the real-time model of the Earth queryable. So that's what we want to get to, and that's what bulk of this work is actually geared towards. So one way to think about all the work that we're doing in Planet is what we call a WebGeo Platform. So we collect a lot of imagery, and we spent a lot of time in the last few years engineering this fairly rich pipeline, which is get the imagery and organize it in such a way that you can then provide access through API. That's what we've done. And that allows for like a range of different applications which are either built on top through our API or in a WebGeo platform. However, the reality is this data is very, very heavy, and heavy in the sense geospatial imagery is very rich and very large. So being able to pull them out of the cloud and put them back in is relatively complex. So our thinking has always been, as you build a WebGeo platform and you do cloud-native processing, you bring the compute and your algorithms and your models all closer to the data, and then you don't deal with the complexities of having to download and make multiple copies of the same imagery. So that's essentially the concept of what we refer to as the WebGeo platform. So towards that end, I thought one of the things that we can talk a little bit about and discuss is disasters. So it's something that impacts all of us in one way or the other. And over the course of the last 18 months, we've had like so many fairly significant disasters happen across the world. And that's one of the areas where there's a huge impact in having access to imagery sources that are in space, primarily because it's very hard for humans to go intervene in disaster regions because infrastructure breaks down. So it's kind of a humanitarian effort that companies like ours can really have a lot of affinity towards. So in the context of building disaster datasets, there are a few things that we wanted to consider. So the first thing we looked at is if you wanted to support any disaster relief efforts, be able to detect them before and after disasters and see change, we can start with areas where there were disasters. So this is a sampling of all the regions where there have been fairly significant humanitarian efforts as well as disaster relief efforts. And this is an example of the coverage in a particular region in Miami, right by the Miami harbor, where Hurricane Irma struck last year between September and October. And what you see there is like the coverage of that region through our satellites. So what you see in the pan-shaped area which overlaps at the Miami harbor is that from the SkySat constellation. And what you see in the rectangular patches are those from our PlanetScope or DOW imagery. So for any particular region here which you sample, you got SkySat and PlanetScope imagery, which are two different resolutions. So through that, we can actually study what it looks like. So here's a mosaic of that same region, which is that from our catalog. So not sure why the resolution of this has dropped so much, but maybe I can just walk you through this, even though it doesn't look very pretty. In deep learning, things often don't till they work. So, if we sample these disaster AOIs, one of the things that's hard to find is if you're looking for a specific object. Often it takes a little bit of effort to find exact instances of it. So collecting data sets is relatively hard because of that particular reason. So one of the first things we do is if we're looking for a particular kind of object, then we start by sampling public data sources where the possibility of finding those kind of objects in our scenes are relatively high. Through that, we can identify scenes that are relevant and then sample those scenes and search within those scenes, which is what we call post-shipping. And once you break down a fairly large scene into smaller chips, we can then go and search within those chips for exact objects, be it cars or be it trains, and then we can then have those annotated by crowd vendors. So that's essentially this workflow. And here's an example. So we start with an AOI, which is that where we wanted to look for like railway lines and trains. So we can then sample all the scenes that are in that AOI, chip those scenes, and then filter them a second time with locations of where train stations are. And through the result of that are chips where there are bounding boxes around trains.
What would be the refresh rate?
Yeah, it's a daily cadence. Yeah. So here's the ontology you can build with that kind of a data set. So if you sample all of the SkySat imagery in disaster AOIs, you can detect these regions around buildings, aircrafts, and watercrafts and miscellaneous objects. So through this, you can build a rich ontology of objects that are detectable and discernible within our imagery. So in the same way, you can do the same thing on PlanetScope imagery. And essentially, this builds the categories in a data set. So you can assemble that. Here are a few examples. And surprisingly, here it looks a little better than the last couple of slides. It's a relief. So what you see here are like planes in like airports and airfields. And then you can also see them closer to like airport runways. It's a lot more visible. Another example is that of trains, railway vehicles. So you can sample them along railway tracks, and you can also sample them around railway stations. Another object in our ontology is like buildings. You can see them in residential areas. You can see them in like different regions like North America. They always have a certain pattern, like the one in the middle. And then in certain parts of the world, like roofs just have a different color. And in satellite imagery, you're always looking at on nadir imagery. So you have one perspective. So one of the exciting things with deep learning and, for that matter, computer vision applications in satellite imagery is you have one perspective. So normally when you look at computer vision applications, you're seeing many different perspectives. And when you try to do object detection or you try to do segmentation on it, you got to understand the 3D model of that object through different perspectives. So the machine essentially needs to learn that. In these cases, even though it's object, it's actually a 2D footprint from one particular perspective on that of that particular object. So I would say in one way, it's not easy, but it's relatively, the thing that's close is the distribution over which you predict or you have to serve deep learning applications is very similar to the distribution over which you train, provided it's from the same spatial environment. So the complexity is always, the satellites are at 500 kilometers above the Earth, and there is something between the satellite and the Earth called the atmosphere, which is very unpredictable. So that's the additional complexity. So the pros and cons of like non-satellite imagery and satellite imagery, when you look at computer vision, is essentially that. So through that, over like a few weeks of data collection, we got to building a data set that has close to like 35 categories and approximately 50,000 samples. And that's where, this is how it places compared to publicly available competition grade satellites. So that pipeline that I showed you earlier, which was in low res, pardon the font, is what enables this to happen. So over the course of the next few months, like one of the things we want to add to that is this essentially object detection or objects. There are land cover types that we can classify. Those all could be added, and that increases the number of categories, and collecting more data is relatively straightforward once you have the pipeline in place. So one of the things I want to talk a little bit about is once you collected the data, then you can try, you got structured data, you can try a lot of deep learning approaches. So the standard engineering workflow is always fairly straightforward. You collect data, and then you manage it in such a form where you can develop a variety of different models and benchmark their performance with each other. And you have certain evaluation criteria depending on the kind of task you're trying to perform. So for object detection, you have a certain set of performance metrics. For pixel level classification, it'll be different. So here's an example of if you took the original pre-expert curated data set, so you just got it filtered through that pipeline, and you got some folks who are very unfamiliar with like satellite imagery to annotate those data sets and create like candidates. If you trained a simple model, it's not simple, but if you trained an SSD model on those for each of the object categories, this is kind of the performance we saw. So what you see in the 3 blue bars for each object category are average precision, average recall, and F1 scope. Okay? So the exciting thing is if you then ran it through an expert curation step, you collected that same data, you got a bunch of people who really understand satellite imagery to look through those images and clean up that data, and you train a new model on those, you see an immediate improvement. So what I'm trying to convey here is that, so this is what it looked like before curation, this is what it looked like after curation, same model. So what I'm trying to say is the modern techniques that you have, fast RCNN, DSSD, SSD, those are all really good and very powerful if you provide it with like clean structured data that is expert curated. So rather than spend all your time trying to innovate on models, we can also be innovating on data sets. So this is a workflow that can drive us towards that. So from there, another way to look at performance characterization is looking at precision and recall for different size objects with different IOU thresholds. So in object detection, you're looking for structured output. When you're trying to get bounding boxes, it's different from classification and pixel level semantic segmentation because you're looking for a particular kind of structure. So the IOU threshold is kind of a very valuable parameter. And in different kinds of applications, you care about different kinds of IOU. So in robotics applications, like some of you are working on, the IOU or the intersection over union of the ground truth bounding box and the predicted bounding box needs to be very precise because you're having like a robotic arm come in and pick something. It cannot be really off because it won't pick anything. So, however, in satellite imagery, especially when you're detecting objects, you don't need very high IOU thresholds. You can deal with lower, primarily because even if you have some overlap, you can create a high recall analytic because you want just enough overlap. So towards the end, when you benchmark the performance as expected as you increase the threshold, you're actually getting to lower and lower precision recall. But you can see, as is obvious, for larger objects, you have very high precision, even at like you have higher precision even at like a 50 or like 80% threshold. So two things that you can take away from this graph for different categorization of objects is, once you have a benchmarking like this, then you know how to pick your IU thresholds. And then secondly, you can always pick something which is like lower and get high recall. So that's essentially what you can take away from here.
Gopal, I don't think I completely understand what you mean by recall. Pressure data or?
Yeah, so recall is essentially saying you didn't miss anything. So if you had a perfect recall analytic, it basically means everything that's relevant was retrieved. And if you have anything lower than that, and precision's the other way around, everything that was retrieved was relevant. So traditionally, we have this notion of accuracy. In the case of like many of these object detection or computer vision applications, you got to look at it from two dimensions: what was retrieved and what is relevant. So these are two metrics that connect into that space. Well, it depends on the application. And so in certain applications, weighing the recall higher than precision makes sense because you care more about not missing anything. If you care about receiving only the right values, then precision is more important. So that's the reason why when you don't know and you want one number and you want to communicate one number as your performance metric, you use the F1 score, which is like the harmonic mean of your precision and recall, which essentially means it'll be closer, it'll be somewhere in between the midpoint of the two and the lower of the two. Okay?
So what difference between this graph compared with the ROC curve?
A good question. So in ROC curve, you're looking at a different set of dimensions. Here, what we're trying to look for is you're using the IUU threshold as your varying parameter, and you're trying to benchmark performance along that axis. Whereas in ROC curves, you're looking at true positive rate and false positive rate and trying to find what the area under that curve is. So there are two ways of looking at performance. So here, if you care more about how much overlap you have between your ground truth and your detections, then this is one way to look at it. So closer to the ROC curve is the precision recall curve. So this is what that looks like. So here what I've tried to do is, if you looked at one particular kind of object, which is ships, we collected a lot of ships data, and you put different confidence thresholds for your object detection, and you looked at it for two different kinds of IU thresholds, you can see how the performance varies. So the interesting thing here is this helps you understand how much energy you actually invest in making a perfect recall, perfect precision analytic. So if you choose to go with high recall, then you know how much more effort you need to put in to make it high recall and high precision. So this is a way to characterize that performance. So as expected, when you lower the threshold and you keep the confidence levels the same, you tend to go higher in value. And that's essentially what you're seeing here. So these are different perspectives on model performance and characterizing that over different size objects, which is actually important. So in object detection, many of the times you care about like not just how well you overlap, but also the size of the objects. So one example is, if you have 3 meter, let's take a more concrete example. If you have like 3 or 4 meter ground sampling distance and you're trying to look for small boats. Small boats normally are 8 to 10 meters or maybe 20, at the most 20 meters long. So they span around 5 pixels. So in 5 pixels, if you're off by 3, then you're at close to 40% IOU. And if you look at that in 2 dimensions, it's less than 20%. So that's the reason why low IOU thresholds are important, because if you miss it by a few pixels, your IOUs are all off. So you don't have as much intersection over union overlap. Yeah. 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 So essentially, Yeah. So yeah, let me rephrase the question. So If you have different zoom levels, what you're asking is, are we detecting objects at those different zoom levels?
So two questions, like the bounding boxes that you build, do you build some sort of a hierarchy at different zoom levels so that if you detected an object at higher granularity, it's reflected higher up?
Yeah.
And then the second thing is the feature maps that you build in your CNN, are those also bubbled up?
Yeah, good question. So the CNNs, especially deep neural networks, tend to be scale invariant, but they're still fundamentally limited by the receptive field at like the early stages of the network. So if the resolution's low there, you won't have anything downstream, which is the reason why using very deep neural networks, you end up doing things like dense-net and residual networks, because you're propagating features downstream. So in this case, I feel you're still looking at it over different zoom levels. You're capturing objects at like different sizes. And if you look at the architecture of SSD and fast RCNN models, they're essentially trying to do that. The reason you have the ROI pooling layers, because you're looking at it with like different aspect ratios over different zoom levels. Any other questions? Okay. So one of the things I wanted to tell you guys about is like the exciting prospect here is you're capturing daily imagery, and you're able to look at change every day. So in the context of object detection, what does that look like? So traditionally, so this is getting back to your question, Noosh. Traditionally, if you look at standard fast RCNN networks, you can think of them as like splitting a deep learning network with a proposal network and ROI pooling in between. So the idea there is you find features or you determine a level at a layer at which you're looking at features in a network, and you come up with proposals derived from those features, and then you bring them all together in the ROI pooling layer along with the original features, and then you can trace it back to the exact locations of where they were in the imagery. So that's how we come up with bounding box proposals. So this is a standard architecture that's been in the works since 2015. It works very well. It's also very complicated. But the exciting possibility here is then you can swap it over different kinds of backbone networks, which is the reason why you hear about fast RCNN inception. So that's essentially the CNN that you use at the front end. So this is used for single image object detection. So if you, in the context of geospatial imagery, and especially at like Planet, we use this internal nomenclature, we call it like a deep stack. So a deep stack is a ground-locked collection of imagery which represents the same place on the Earth over time. So if you were to feed that kind of a stack into this network, you need to make a few changes, but the network can still work. So that's essentially running the image stack through your original set of convolutional neural networks. But then you introduce something which is like a 3D convolution on all the feature maps. So that helps you create something closer to a mosaic of features in the feature map space. So you're essentially building a mosaic from the tensors at the output of your convolutional neural network. And that allows you to do object detection downstream for objects that are only present in one frame but not present in the others. So here's an example. So this is a target frame, which is the most recent frame in which you want to do object detection. And then we create a temporal image. So a temporal image is fairly simple. It's a three-channel image where each channel is a grayscale version of the imagery, and then you stack them up. So in this case, like red refers to the current time, and green refers to the last timestamp, and blue refers to a previous timestamp. Okay? So through this, you can actually see which objects are present and which objects are absent at different instances of time. And then you run it through a network like that, and you can see that there's a lot of focus on that one particular ship on the lower left image that the regional proposal network fires more on. So these are some early experimental results. We're actually submitting some of that material to a journal in the coming months, so stay tuned on that. So Okay, I talked to you about spatiotemporal object detection. I spoke to you about catalogs. So here's something which is a lot more closer to us in space. So this is the port of Oakland, and you can see that from satellite imagery, you can see the shipping containers, you can see cars, ships, rail carriages, and buildings. It's a fairly diverse and rich port, very close to us. But over the course of a year, this is what it looks like. So this is a time-lapse video of what's happening on the ground over the course of a longer period of time. So you can see ships going in and out. You can see containers getting embarked and disembarked, and you can see traffic on the roads. So that leads us to a fairly rich set of applications. You can detect ships like I just described. You can correlate that with signals like AIS to know where exactly they're headed and where they're from. You can correlate that with traffic patterns on the ground, and then you can connect them with telemetry data to create essentially a real-time model of the Earth. And the satellite imagery and derived feeds from there can be the baseline for delivering those kind of quick analytics. Another example is that of the airport in Beijing. So here's an internal tool that we've created to aggregate detection. So what you see here at the bottom panel is essentially detections of the number of planes that arrive at the Beijing Airport at a particular instance in time every day. And you go from imagery to detections on the ground, and at that point, you're only caring about derived signal, and imagery is just a way to verify that signal over time. So that's the kind of application that connects into end customers who don't really care about satellite imagery, but they want pure, pristine proof of record signal. So this is the way to get to that. So here are some active research frontiers from what I described to you. Capturing observational variability is just central in everything dealing with satellite imaging. With the exception of radar imaging, all electro-optic or optical imagery has this problem of atmospheric interference and varying conditions. So over the course of like a year, like the imagery varies in color just because of like the atmospheric conditions at that point. So being able to understand that, being able to mix and match different resolutions towards more richer set of analytics, being able to tip from like a lower resolution imagery and be able to do follow-on analytics at higher resolution is a very rich application. Yeah, you had a question? So object detection and time lapses, again, another very exciting area. And being able to do, so one of the interesting papers at CVPR this year was around being able to do bounding box creation and imagery annotation using reinforcement learning. So you essentially study the patterns of a human annotator, and then you train a machine learning model to do that. So it's fairly promising in the sense most of the times the one human piece in this entire loop was the annotation and the expert curation. So if you can find sensible ways to make the load on that lighter, you can build more richer data sets over varied geographies, over varying conditions, and constantly roll that into online learning system that can enable your performance to constantly get better. And then I didn't talk about land cover a lot. That's a whole different ocean of work and many exciting possibilities there. So being able to do that right allows you to get to geovisual indexing, being able to sort and search through many interesting pieces of imagery with the same visual cues is something which I believe can open up like a range of different applications. So all this gets into the realm of what we call queryable Earth, being able to see patterns of change, index them over time, and be able to perform those kind of analytics in a generalized context because of the fact that we capture the Earth every day and we have all the context of the globe. So that's where we aspire to be. And if the scale and scope of this effort is exciting to you, you should definitely talk to me because we're actively hiring machine learning engineers, data pipeline engineers, analytics application engineers towards making all this stuff a reality. We serve into a range of different industries. And the thing that brought me to Planet is the fact that, over the years, since deep learning has like taken off, we've seen a range of different applications come to surface, but the possibilities there are like definitely rich, and a lot of that work happens in the open community. And over the course of time, models become commodity. Data is what holds the real value. So when you have gated data sources, you have a native way towards building moats around your businesses. So that's one of the things we're all excited about at Planet, and towards making like a bunch of different applications that can potentially help humankind. So that's pretty much what I have. I'm happy to take any other questions that you have.